Shall I start? Okay. Okay, so the agenda for today is to talk about tree amplitudes and recursion relations. There's a chance we'll get to the BCJ relations too, but maybe not. We'll see. The color kinematics and relations to gravity. Are there any questions from last time? The exercises all sort of make sense after a little bit? Okay. So I just want to put up a few things we did at the end of last time. We talked about the fact that all amplitudes have a particular kind of scaling, which we call little group scaling, which allows us to count. We're using these two component spinor variables, the lambdas and the lambda tildes, everywhere. So all the amplitudes are going to be functions of lambda and lambda tilde. But they're going to have a little sort of excess lambda versus lambda tilde in them, which is characterized by the helicity of the state. For example, there's an external wave function or state factor for a helicity plus fermion, which is a lambda tilde, given chirality of the external spinor. And if it's helicity minus a half, then you get the opposite chirality. So if you imagine a transformation where you scale the lambdas in one way, like e to the I phi I times the ith lambda multiplied by e to the phi I for the ith lambda, and then the lambda tilde the opposite way, e to the minus I phi I. So you can ask, how does the amplitude transform under that transformation? And it has to pick up a certain phase. I didn't write the exact phase down, but basically, if you choose to think of lambda tilde as being equivalent to a 1 over lambda and vice versa in a formula, and then you count sort of the net number of lambdas, you find that the amplitude scales like lambda minus 2hi. So just to check that out, this scales like a 1 over lambda. So for h equals a half, we get lambda to the minus 1. This one has h equals minus a half, so we want it to go like lambda to the plus 1, and it does. And then the same thing happened for vectors. I wrote down a formula for the vector polarization yesterday, which has a lambda tilde in the numerator. And I asked you to check that it was transverse. So that means that epsilon dot k is 0, where k is lambda alpha dot. So basically what happens when you do this contraction is this lambda tilde alpha dot gets contracted with a lambda beta dot that comes out of the k. And this is, well, it's a 0 by antisymmetry. So that's how this formula gets to be what we think of as the natural gauge condition on a vector polarization, that epsilon dot k equals 0. It also has a bonus symmetry that it's perpendicular to q, this arbitrary vector. So it's perpendicular to sort of two vectors at the same time, and you can use that property sometimes. And somebody asked afterwards, well, to get the scaling that went like 2 powers, like twice this, you put a lambda in the denominator. Why didn't you put another lambda tilde in the numerator? And the reason is that you want these to make properly normalized states. And you usually normalize fermions a little bit differently, sort of not to 1, but bosons you always normalize to 1, or technically this should be a space-like vector with minus 1 in the dot product. And it's that requirement that forces you to put a lambda downstairs. When you go through and calculate epsilon dot epsilon star, you'll find it's 1, up to maybe there's a root 2 or something in here. I forgot. Anyway, so that's why you need a lambda downstairs and a lambda tilde upstairs. And then for h equals minus 1, you get the opposite behavior. And we could also do gravitons that way. A graviton is a spin 2 particle, and you basically can produce the graviton tensor polarization in this spinor language just by multiplying together two of these plus helicity vector polarizations. That'll give you a helicity +2 tensor external state for gravitons. Any questions about that? Once we know that the amplitude has this kind of scaling, which we could also write, because lambda tilde is scaling the opposite direction, we could write it like this with the opposite sign. Then it's just a simple matter to constrain the form of the 3-point amplitude. You put generic exponents up here, and you have 3 equations for those 3 exponents to get this scaling right. And the unique solution is to choose those exponents like this. So should be h3 minus h1 minus h2 for this one, and then you can permute cyclically 1 goes to 2 goes to 3 to get these other guys. And we checked last time that scaling works. So that's a formula for the 3-point amplitude. However, this is another formula for the 3-point amplitude. Because these square brackets are made out of those lambda tildes, and the lambda tildes scale in the opposite direction. So we have an alternative solution in which we just flip the sign of the exponent and use the lambda tildes instead. So now we have a question, which formula are we supposed to use? Remember from last time there were 2 complex kinematics. 2 3-point kinematics. So one was where we chose all of the ij's to be, all 3 of them to be 0, and the ij's are non-zero. And the second one was the conjugate, so all of the ij's were 0, and then these guys were non-zero. And the only reason we could have these solutions at all was by using complex momenta. Otherwise, all of them would be 0. So obviously, this one is one we would use in the first case, and this would be one we would use in the second case. So let's, the distinction between the two, once we pick the external helicities, is going to be the overall dimension. What is the dimension of ij? The mass dimension, or scaling with momentum k. Well, we know that if we take ij, ji, well, these have the same dimension, and that's sij, which scales like 2 powers of the momenta. It's a ki dot kj. So it scales with momentum like 2 powers. So each of these things, they scale like k to the plus 1. Okay? Because they're square roots of Mandelstam variables which scale like k squared. So this thing, if we add it up, we have k to the sum of these powers, which is k to the minus h1 plus h2 plus h3. On the other hand, this one here, because we flipped the sign, scales like k to the plus h1 plus h2 plus h3. Okay, so let's do an example. Let's suppose that h1 equals h2 equals h3 is equal to -1. So we're going to have three vectors, and coming out of a three-point interaction, they all have minus helicity. So if we use the top formula, then we get that A3, 1 minus, 2 minus, 3 minus is equal to some number times 1, 2, 2, 3, 3, 1. Question mark. But we have another solution using the bottom line where we get these guys downstairs. So what's the right answer? Sorry, thanks. I'm so used to writing squares when anyway. Right, that's right. Good. So how do we figure out which is the right answer? Well, we think about the dimensions of amplitudes. Now, you may not be used to what the dimension of the three-point amplitude is, but remember that if we have a dimensionless coupling like Yang-Mills, and you guys looked at the Feynman rules for Yang-Mills, so this Feynman rule has an eta mu nu times a k, a difference of a couple k's. Anyway, all I want to know is that when you have a dimensionless coupling, like a G, this goes like k to the plus 1. And that's the three-point amplitude. So we're looking, if we want Yang-Mills theory, we're looking for something that scales like k to the plus 1. And this scales like k to the plus 3. And this scales like k to the minus 3. So this can't be Yang-Mills theory. It turns out that if we have, to make the overall dimension 1, we can put a 1 over m squared there. Or let me call it 1 over lambda squared, because it's sort of like a cutoff. So this amplitude is not produced by Yang-Mills theory. What it's produced by is a Lagrangian that contains 1 over lambda squared times the dimension 6 operator, which is g mu nu, where g is the gluon field strength. Now these should have indices A, B, and C, and an FABC out front. So this has the wrong dimension to be Yang-Mills theory. And this one's even worse, because to make it have the right dimension, you would have to put a mass in the numerator, I guess lambda to the 4th. And there's no way to couple vectors together with such a with that dimension. If you have lambda to the 4th in front of your operator, it's basically the cosmological constant. So this thing is just sick. It's not local. It's too singular. Okay, so in the case when all the helicities are -1, we have a candidate amplitude, but it's not an amplitude for Yang-Mills theory. It can be the seed of an amplitude that has QCD interactions in it too, but it has the wrong dimension, and so you have to have a local operator here. So you can actually classify local operators of higher dimensions by classifying different kinds of amplitudes. In fact, amplitude people don't even like to talk about Lagrangians. The only reason they talk about Lagrangians is to talk to other people. Okay? Otherwise, we don't really like to say the word Lagrangian. Okay. By the way, there's another thing you can check here, which is I didn't write any color factors down here. Okay? And most vectors you know about have color factors. Not photons, but gluons do, for example. And one thing you know is that bosonic amplitudes have Bose symmetry, right? So whenever you exchange two of them, you should get the same result. Let's exchange two of these gluons, like let's say 1 and 2. Okay? What do we get when we exchange 1 and 2? So this becomes 1, 3, and this becomes 3, 2. Those are in the wrong order. Remember, these spinor products are antisymmetric. So they're also minus signs, but there are two of them here, and then when we exchange these, there's one more. So this picks up a minus sign. It's a bosonic amplitude. It's supposed to have a plus sign. But we didn't put in the color factor. So what we know is that for this amplitude to work, we need a color factor that's antisymmetric under exchanging the colors of 1 and 2. Because we exchanged the particle labels and the helicities were the same, but we need a minus sign from color. But that's okay because the color factor is FABC. So, in other words, you could not write this with a symmetric color tensor. There's something called DABC. You can't use it in this case. The symmetry tells you it has to be FABC. Of course, the operator analysis would tell you that too, because these G's field strengths are antisymmetric. And when you go through the symmetry properties of that, you see it has to be FABC also. But you can see it from the amplitude that this really is going to need, has a hidden FABC, which we stripped off when we wrote down this color stripped amplitude. Okay, any questions about that? So now we should write down the actual Yang-Mills amplitude. It doesn't generate amplitudes with three helicities of gluons that are the same. Instead, it only generates helicities that are where one has one value and the other two have the opposite value. Well, I probably erased the key formula, but as usual. We usually strip off the G anyway, but if you plug into that formula, when H1 is equal to -1, H2 is -1, and H3 is +1, you see that you need to, well, you need to put the 3 downstairs twice, and you need a net 1 upstairs twice, and 2 upstairs twice, and this does the job. So that's the Yang-Mills amplitude. Sometimes it's written in the form with an extra 1, 2 upstairs and downstairs, so that the downstairs has a cyclic symmetry. And this would be called the Park-Taylor formula for the 3-point amplitude, except that Park and Taylor only really considered, they didn't think about the complex kinematics, and they only considered their formula, which I wrote down on the first day. They only wrote it down for n greater than or equal to 4, and I think maybe Ed Witten first wrote this down in like 2003, the fact that it also holds in the complex kinematic 3-point case. So that's one amplitude. So there's also an operation parody, which flips all helicities between plus and minus. And the way parody is implemented, if you looked at the formula for the polarization vectors, it corresponds to exchanging all lambdas and lambda tildes, at least up to a sign, overall sign. So we can then just write down the, well, sometimes there's a minus sign depending on the state convention. So the formula for the other helicity case is with 2 pluses and 1 minus, has exactly the same form, but the angle brackets and the square brackets have been exchanged. Any questions about that? So these 3-point amplitudes, although they're not physical for real kinematics, they're going to be the seeds for higher point amplitudes through recursion relations. You had a question? It's just a tradition in how you normalize the phase of tree amplitudes. In some sense, tree amplitudes are supposed to be real, but they're not very real when you choose helicities, because the polarization vectors for helicities, they have eyes in them. But there's a convention to make the tree amplitude be I times real if you chose a linear polarization. And anyway, that is just some convention. And as long as you always keep your internal phase conventions consistent, it doesn't really matter too much. Any other questions? Yep. I put it in parentheses here, indicating that it was about to vanish, because when we gave the color decomposition, remember in the color stripped amplitudes, I pulled it out. I just wanted to remind you of it. Well, maybe it was to remind myself to point out that the dimension, which I forgot to do, the dimension of this, you see there's 3 upstairs and 2 downstairs, so it has k equals k to the plus 1, and that's what we want for Yang-Mills. Okay, so that means that there should be a dimensionless coupling in front, and so, but then we take it away when we use the standard color decomposition where we removed it at that step. Any other questions? So gravity actually works exactly the same way, in the sense that we saw that there was sort of a unique answer given the external helicities. The helicities for gravity are plus or minus 2. They're just double that for Yang-Mills. So the gravity amplitudes should be just at the 3-point level, they should be the exact squares up to phase conventions. So we can just write down that M tree 1 minus minus, 2 minus minus, 3 plus plus. This is just a reminder that it's helicity plus or minus 2. So it just be the corresponding tree amplitude for Yang-Mills up here. Squared. So just take this thing and square it up to, again, some I phase convention, which you can decide to do. And then the same thing when we have the opposite helicity case. You can make a state taking the tensor product of a plus polarization vector and a minus polarization vector, but it has to have helicity 0. And it can be associated with some states that are naturally there in supergravity theories called the dilaton and the axion. You have 2 choices because you have plus on one and minus on the other, or vice versa. So those 2 states are spin 0 states. And so actually, when you double copy pure Yang-Mills to get gravity, you have a plus 1 state and a minus 1 state. And when you tensor that together and add up the things, you get minus 2 plus 2, what you want for gravity. And then you get these other 2 guys, which are called the dilaton and the axion. And you usually don't want them if you're doing things like classical gravity for LIGO. So you'd like to get rid of them. Turns out that because of how they couple, if you calculate a tree amplitude with all gravitons on the outside, then they automatically decouple on the inside. But if you try to do something like LIGO physics, where you have some black hole source, it's not quite so easy to decouple them. And it's also harder to decouple them in loops. So they can be decoupled in supergravity, or in supergravity you actually want them, and it's often in extended supergravities it's not such an issue. Yeah. We've only used the special properties of the three-point kinematics. And the fact that it's uniquely, the three-point amplitude is uniquely dictated by the helicities to show it for the three-point case. But we haven't shown it for this case yet. That comes later with the BCJ relations and some argument about double copying or from string theory. But no, I didn't really, give you an argument yet for endpoint amplitudes.
What about three-point? How do we know that three-point amplitude for gravity is just square?
Remember, we derived a general formula for the three-point amplitude as just a function of the helicities. And so now all you need to know is that the helicity for the gravitons is twice the helicity for the Yang-Mills, and then you plug into the formula and you see it's exactly the square. Any other questions? Yep. Oh, yeah. Yeah, so remember this, let's see. Yeah, it needs a 1 over m. And it's 1 over m Planck. And the gravitational coupling that people use is something called kappa. But to connect to what other people use, you need to know that kappa squared goes like g Newton, like 1 over m Planck squared. So the Newton constant for gravity is a force, so it's an exchange of a graviton between two objects. And when you calculate it with a Feynman diagram, you put a kappa there, and kappa squared is supposed to give you g Newton, which up to h bars and c's is 1 over m Planck squared. So the dimension of the gravity amplitude is the square of Yang-Mills, so it's k squared. But any three-point amplitude for bosons should go like k. So that's why I need a 1 over m Planck, because I still want the same dimension for the graviton amplitude. I have a k squared, I need 1 over a mass. So I need to put in front a kappa, which goes like 1 over m Planck, to fix the dimensions. And that is the right answer, because the coupling for people who do quantum gravity is kappa, but people who know about Newton's law, that's kappa squared, because it's a force between two external objects. That make sense? Okay, so anyway, this is not a proof of gravity equals Yang-Mills squared, but it's highly suggestive, and we come back to that later. But now I want to turn to a way of constructing endpoint amplitudes in gauge theory of multi-gluon amplitudes using recursion relations. But first I just want to write over here a few identities among these spinor products that we'll need later. And some of these I wrote already. So these angle brackets are always 0 if it's the same particle, and that's because of the anti-symmetry when you exchange the two particles. And the square of the ij with a square bracket ji is the Mandelstam variable, is the Mandelstam invariant. So we need to write one other equation, which is in an endpoint amplitude we have momentum conservation. So the sum I equals 1 to n of the momenta ki is equal to 0. We're going to write the k's as these alpha alpha dot matrices, and then we're going to contract them with I'm going to take this equation and I'm going to contract it with lambda alpha j lambda alpha dot L. And when I do that, I'm going to get a relation which is the sum I equals 1 to n of the angle bracket j I angle bracket the square bracket I L equals 0. So that's an important identity. You see, when I contract these, and this is really just the product of lambda I alpha with lambda, that's a lambda tilde. Lambda tilde, there's a lambda and a lambda tilde. So I contract these to get the angle bracket, and I contract these to get the square bracket. So that sum is 0. So then there's one more identity that is used universally, which is the Schouten identity. And it says that if you have 4 of these spinors and they appear in pairs, and you take the difference of these two combinations, then you can rewrite it in terms of the third way of contracting them together. So as an exercise in understanding the meaning of these spinors, you can show this. And the key to showing it is to first show, or first use the fact that lambda k is lambda k is a linear combination of lambda I and lambda j. Why is that? Well, this alpha only runs over 2 indices. So you should think of lambda I, lambda j, and lambda k as 2-dimensional vectors. They live in a 2-dimensional space. There's just 2 components for them. If I have any 2 vectors, then I can use them to span the 2-dimensional space. So the next vector, lambda k, must be a linear combination of those 2. So now what you have to do is compute C1 and C2, and you were going to do that by contracting with both sides of this equation with lambda I and lambda j. And then after you figured out what C1 and C2 are, contract this relation with lambda L, and then you'll get the Schouten identity. You mean that there'll be a singularity if lambda I and lambda j are the same? Yeah. But for the purposes of deriving the identity, you can assume that they're generic. And the identity will also work when they're the same. It's just there will be, it'll be when you set j equal I, this term vanishes, and you can check that using the anti-symmetry, it's still true. Okay, so those are the basic identities that you need to manipulate these spinor products. And it's actually, sometimes it's non-trivial to simplify an expression made out of the spinor products because these identities are kind of non-linear. You're not sure which one you're supposed to use. So sometimes people don't bother simplifying things if they just show numerically that it's equal to another simple representation, stuff like that. Okay, so now we're going to go on to the talk about recursion relations. But I need to say a couple words about factorization, which is sort of locality. So at tree amplitude, or in any amplitude, you should think of a bunch of plane waves coming in and going out in a particular region of space-time. But in some cases, the amplitude could really be something happening in two different regions of space-time under special circumstances. And if it's really happening in two different regions of space-time, then there should be some long-distance particles carrying the information from one region to the other region. At tree level, that information can only be conveyed by a single particle. So I'll just use straight lines because I don't care whether these particles are gluons or whatever. But there's a special configuration where the amplitude can split into things that are happening in two different space-time points. This particle that conveys the information between here and here, it has to be able to propagate a large distance, so it has to be on its mass shell. So if we have momenta k1, k2, up to, well, maybe bad choice, but k plus 1, k all the way to kn, we have an endpoint amplitude. But suppose that the momentum capital K 1 to K, which is K1 plus, suppose that's going to 0. These are all massless particles, just for the sake of argument. Then when this thing goes to 0, that's the conditions under which this amplitude factorizes. Under this condition, the amplitude, so we have AN, and it's being approximated by something that has K plus 1 particles here, because we have 1 to K, and then we have this intermediate particle. Let's call it capital K. So we have K plus 1 particles here, and if you calculate, you have N minus K plus 1 particles here. So this amplitude AN factorizes into a product of two amplitudes with smaller numbers of legs. And it should have a factor corresponding to the propagator, which is almost equal to 0 in between. So that's sort of a fundamental property. And we can see in this property the possibility of deriving a recursion relation. If we can use this information to construct the full endpoint amplitude from the different ways it factorizes, then we will be able to use lower point information to build up higher point amplitudes. That's the whole idea behind a recursion relation. Yep. The error term? Plus order 1 terms as k squared goes to 0. Okay, so now I need to say a couple words about helicity when you have two amplitudes. So when I wrote down these helicity amplitudes before, I didn't quite say it, but I was using an all outgoing helicity labeling. in the real world, you have incoming particles and outgoing particles. We pretend when we write these formulas that all the particles are outgoing. If they're incoming, you're supposed to interpret the helicity as being the opposite of what it actually is. So, for example, if I write a 4-point amplitude with 1 minus, 2 minus, 3 plus, 4 plus, I can write a single formula that doesn't care which particles are incoming and which particles are outgoing. But it really corresponds to things like if what particles 1 and 2 are actually incoming, then the formula really corresponds to them having plus helicities. So a configuration like this. Or I could take 1 and 3 incoming and 2 and 4 outgoing. And in this case, this would be, it would correspond to this configuration. Okay, so those are the rules that we use so that we can write formulas that are what we call crossing symmetric, and we don't have to rewrite them depending on which particles are incoming and which are outgoing. Okay, but that means that when we use this kind of labeling, where some of these are plus, minus, we have to ask what happens when we write down a helicity for something crossing this cut. So whenever we put something across the cut, if it's plus on this side, it has to be minus on this side. Because it's the same particle, if we think of it as outgoing this way with helicity plus, then we have to reinterpret it as incoming, which means we have to reverse the helicity convention. So whenever you cross a cut, you get to put a plus on one side, you have to put a minus on the other side. Okay? Okay, so now we're going to do the BCFW recursion relation. And it's called an on-shell recursion relation because it only requires lower point on-shell amplitudes. There were other recursion relations that people had written down earlier. So Behrens and Gila wrote down a recursion relation earlier, but it was off-shell. It used things that are in intermediate steps that are off-shell and not gauge invariant. Doesn't mean it's not a fast recursion relation. It's very good. Okay, so we want to take this tree amplitude and we want to promote it. We want to embed it in a one complex parameter function family of amplitudes. Really, it's a multivariable complex parameter function because all these lambdas, we could think of them as being complex. But multivariable complex analysis is very hard, whereas one-dimensional complex analysis is very easy. Cauchy figured out how to do it a long time ago. And we're just going to use Cochise Theorem to analyze the analytic structure of this amplitude and use that to derive the recursion relations. So how can we make the amplitude depend on a single complex parameter? So what we think about is an endpoint amplitude, and we want to modify the momenta of just two lines, 1 and n. And we're going to do that by deforming the spinors that go into it. And I'm going to call this thing an n, 1 shift. The n and 1 indicate that these are the two lines that I'm going to shift. This is a BCFW shift. And the square bracket means that I'm only going to touch the lambda tilde part for the n case, and I'm going to shift it to lambda n, the original one, minus z, there's the complex variable, lambda 1 tilde. And this thing is sometimes, the shifted variable has a hat on top of it. Whereas lambda n, it's going to stay the same. And then lambda 1 is going to get shifted. And lambda 1 tilde is going to stay the same. Okay, so those are the 4 transformations, and all the other spinners from 2, 3 up to n minus 1 stay the same. Now, notice these are linked in a particular way. Why are they linked? And that's for momentum conservation. Remember, momentum conservation says that the sum of all these lambdas times lambda tildes is 0. We didn't touch any of these guys, so we better make sure that the contribution to momentum conservation from legs n and 1 stays the same. So that's lambda 1 times lambda 1 tilde plus lambda n times lambda n tilde. And that goes to lambda 1 plus z lambda n times lambda 1 tilde plus lambda n times lambda n tilde minus z lambda 1 tilde. So the part that depends on z has a plus z lambda n lambda 1 tilde minus lambda n lambda 1 tilde. It cancels. Okay? So we cleverly arranged this sort of shifting one spinner by the other and this one by the other with the plus and minus sign. That's just dictated by momentum conservation. Also, we should make sure that we kept the external particles on shell. But that's just a consequence of the fact that the shifted momentum factorizes into a product of a row vector and a column vector. And that's the condition to have a vanishing determinant of the matrix, to have the k squared equals 0. So this was automatic by working with these spinners. The corresponding momentum still has a factorized product structure, so it must stay massless. It's going to be complex now, but that's okay. Okay, so that's the shift. So we maintained momentum conservation thanks to this equation, and also k1 hat squared of z equals kn hat squared of z is always equal to 0 thanks to factorized 2 by 2 matrices. So that's true for any z. Oh, by the way, so this shift vector, another way of thinking about it is that the shift vector v alpha alpha dot, which is lambda n times lambda 1 tilde, because it has 2 factors, when you dot it with k1 or you dot it with kn, you always get 0. No, there's no restriction like that. Like one of them could be a quark and another could be a gluon. We're just going to give the gluon example, but it's not necessary. There's some. In fact, we'll see it's easiest to show that this how this works when the 2 gluons have opposite helicity. So they're also not identical because of that. We're using analyticity. The fact that amplitudes are not just arbitrary values of real variables, but when you promote them to complex variables, they have analytic properties. They have a limited set of bad behavior. They just have poles in the z-plane, because we know that the poles and amplitudes are from propagators, 1 over p squareds, and when we think of those as a function of z, we just get poles. You could try to do the same thing at the loop level, but then you have branch cuts in amplitudes at the loop level, and then you will get branch cuts in z, and so then it's different analysis. Okay, so yeah, I just wanted to mention, suppose we have 2 particles. Oh, I forgot to say one other thing. Because this shift vector, you can show that v squared involves, when you calculate v squared, you get this. These 2 guys get contracted together, but that's 0. This is also 0. So I should have also said v squared is 0. So we have a light-like vector, and it's perpendicular to 2 other light-like vectors. You guys know that when you collide 2 massless particles, you can always choose the center mass frame. So you have a light-like vector here and a light-like vector here. So think of those as particle 1 and particle n. So now we're looking for another light-like vector that's perpendicular to both of these vectors. Since they sort of span the time direction and the z direction, that perpendicular vector should be in the x and y direction. How can you make a light-like or massless vector that's also in a spatial, purely spatial direction? The only way to do it is make it complex. So this shift vector has to be complex. You know, so if they were coming in like this, and this is the x and y direction perpendicular, it would be some vector like 0, 1, I, 0, if this is time, x, y, z. Yeah. Okay, so, all right. So the basic idea is that we now have this amplitude as a function of z, and we need to think about its singularities in the z-plane. Actually, to be clear, let's try to use the following formula. So we want to consider the amplitude as a function of z and take a contour integral around a very large circle. And if A falls off fast enough at infinity, then the contribution from the large circle at infinity will be 0. But on the other hand, it'll be equal to the sum of the residues by Cochise theorem. And there's one residue at the origin coming from this z, and that's good because when we set z to 0 again, that gives us our original amplitude. And then we'll get contribution from residues at finite values of z. So let's label those by k, and we'll need to compute the residue of an of z over z at z equals zk. So this tree amplitude is also a sum of Feynman diagrams, and the only places it can become infinite is when the intermediate propagators vanish, and that's in accord with this space-time picture of factorization that I drew earlier. It can only happen when intermediate particles go on shell. And so the poles at finite z, these poles at zk must correspond to a diagram like this. This shifted momentum we indicate with a hat. There's a momentum flowing through here, which, if it's flowing downward, must be, this is the sum of momenta from 1 to k, with a capital K here. And then we have, this is a color-ordered amplitude, so the ordering goes from 1 to n, like that. And n is also shifted. So I drew the factorization channel vertically instead, but the idea is that as you explore in the z-plane all the different, you can find a number of factorization channels where k1k squared as a function of z, when you set z equal to zk, it's equal to 0. And that is what we're going to use to do the factorization and write the residue in terms of products of lower point amplitudes shifted to complex momenta. Any questions about that? Yeah. No, that's the next step. So the next step is to show, because I had a question mark there, that there wasn't any contribution from infinity. I just did that so that somebody would ask a question about it. Yeah. So, so to look at z goes to infinity, we're going to go back to Feynman diagrams, but we're not going to evaluate them. We're just going to power count them. Okay? So, yeah. Oh, sorry. That's supposed to be a plus. Thanks a lot. Sum of all residues. One residue is at, z equals 0, and the rest of them are going to be coming from factorization. Thanks, Andreas. Okay, so to check the z goes to infinity, we're going to assume that n carries minus helicity and 1 carries plus helicity. And in almost all amplitudes, you can find a particle with minus and the other one with plus. And we'll see that the other ones, or you'll show that the other ones vanish. But anyway, for the moment, let's just assume that particle n has negative helicity and particle 1 has positive helicity. In that case, let's look at epsilon n minus. The polarizations for minus helicity particles have a lambda on top and a lambda tilde on the bottom. I'm not showing the reference, the Q's, because it doesn't matter for this argument. All I want to do is see how these things scale. Remember, lambda n stayed fixed, but lambda n tilde went to minus z lambda 1 tilde. And as z gets very large, so we're taking z to infinity, that goes like 1 over z. That's why I picked n to be minus, because I knew that this polarization vector would fall off like 1 over z. And epsilon 1 plus is the other way around. It has a lambda 1 tilde in the numerator and a lambda 1 in the denominator. And the way we did that shift, the lambda 1 goes to lambda 1 plus z lambda n. So I get another 1 over z from the polarization vector down here. So now I'm going to write a Feynman diagram that goes between n minus and 1 plus. And there can be a bunch of other stuff coming off of it, but none of that really matters. What matters is what's happening along here, because this is where the big momentum shift is flowing. So I have a bunch of propagators and vertices. I always have one more vertex, then I have propagators. And remember, the vertex goes like k, and the momentum shift is proportional to z. And if I'm looking anywhere along here, that momentum shift, it's shifted by z times that v alpha alpha dot. So this thing will scale like z. In the denominator, I have a 1 over p squared, and that contains something plus zv squared. It might look like it goes like 1 over z squared, but the z squared term multiplies v squared, and v was a light-like vector. V squared is 0. So this does not go like 1 over z squared. It goes like 1 over z times whatever x is dotted into v. Because v squared is 0, we don't get the z squared term. Okay, so the propagators, every propagator falls off like 1 over z. Every vertex goes like z. So in this chain, every time I have a propagator and a vertex, that cancels. The z cancels the 1 over z. But I have, after doing this, I always have one leftover vertex. You can see there's one more vertex here, 3 vertices and 2 propagators. No matter how many you put in, there's one extra vertex that goes like z. But fortunately, I had 2 external state factors that went like 1 over z. So the final dependence of this amplitude is z from the excess propagator divided by z squared goes like 1 over z. So if a goes like 1 over z at large z, and I have an extra 1 over z from here, I have dz over z squared, and that converges at infinity, and I get the 0, so I get to take away this question mark. So that's the one helicity case that for gluons only, that you can prove directly using Feynman diagrams. It actually is true for many other helicity configurations, but it's not so obvious how to do it straight from Feynman diagrams. Any questions about that? Anyway, the bottom line is you power count the behavior when one line has a very high complex energy proportional to z, and you get that result. Yep? Correct. If n is plus and 1 is minus, then you want to do the 1 comma n shift instead of the n comma 1 shift to show the convergence works. If you by mistake did the n comma 1 shift, that is the one case where the amplitude actually does diverge out at infinity, and so you would have to take into account the boundary term, which is something you're trying to avoid. If both helicities are plus or both are minus, although you can't see it from the diagrams, it turns out that the boundary term vanishes. So there's only one bad case, which is the one you identified where you got them backwards from this case. Okay, so now the only thing left to do is to evaluate minus the sum of the residues, and that will give us this amplitude. Okay? So first of all, we have to figure out what zk is in the kth term. So 0 is, we're shifting k1 to the point zk, but the definition of this k1k is that it has all these other guys added to it. You have to add k2 all the way up to, so we have to solve this equation for zk. So it's this shift came from lambda 1 plus n. Yeah. I know, I kind of screwed this up. The k underscore is just an integer. It's an index. These k's are momenta.
No, I mean, there are two indices, one for zk and another for k.
Well, this k is the same as this k. As you change the integer labeling where you factorize the amplitude, you get a different pole in the complex plane.
So we know exactly how many poles we'll get.
So if the amplitudes are color ordered, then this has to run from 1 to n. And so there's basically k roughly runs from 1 to n, except the real bottom cutoff, the smallest value of k you can have is 2. Because there's no factorization on it, a 2-point amplitude doesn't exist. First case you get is 2. So that's k min. And k max is n minus 2. If this is n minus 2, then you have n minus 1 and n on the top. You have a 3-point amplitude on the top. So that's the, I should just write it here. Okay? Good question. So this is zk, the shifted part evaluated for z equals ek, times the shift vector v, which I called v, which is also lambda n lambda 1 tilde, and then this unshifted vector k1k. So sometimes we use a little shorthand. Let me, maybe I should write it like this. So if, suppose V is the sum of some K's, any collection, we can write AVB as the sum over I of AI IB. It's just the shorthand for wedging a vector between two spinors when the vector is a sum of massless vectors. When we evaluate this square, the zk squared term multiplies the square of this light-like vector, so it's 0. But then there's a zk term that multiplies an n from here, a k1k, and then a 1 with a square bracket. And then there's the last term, which is just the square of k1k. And this should be equal to 0. So we can derive zk is equal to minus k1k squared over n k1k 1. So now we know what value of z to evaluate the amplitude at. And but we need one other thing, which is we have a 1 over p squared propagator, which is going to give us the residue itself. Oh. Remember that in the factorization formula, there's also a 1 over k squared in the vicinity of zk, but not quite there. So, oh, and there's also a factor of z from here that's downstairs in the residue formula. So we need to look at this quantity z k1 squared of k a little bit away from z equals zk to do the residue. So if you go back to this formula and take z a little bit bigger than zk and do the first Taylor expansion, you find that it doesn't quite vanish. It's trying to vanish as z goes to zk, and the coefficient in front has this behavior. And so it gives us a minus k1k squared, the unshifted propagator.
Why are you considering z k like k squared? Where did you see?
This z?
No,
It came because I'm computing the residue. And this amplitude, an of z, much earlier I showed a factorization formula which had a 1 over k squared in it. It comes for the propagator. But I also have a z downstairs. So the thing I really want to expand in the vicinity of z equals zk is a z from this formula and then a 1 over k squared from inside this an of z. So that's why I look at this. So then you show that, and this z, of course, just gives me a zk when I take z near zk. And this thing's vanishing, and it has that cross term in it. You can kind of see it right there. And those two combine through that equation to give me this factor of the unshifted propagator. When you take that into account and keep track of some signs, and there's really an I for the propagator, you go back to that residue formula and you find that an is an of 0, and there's a double sum. One sum is just the possible helicities for massless particles, plus or minus. Then there's this sum over k that we just talked about. And then there's the factorization formula into two amplitudes. I'm not bothering to show all the helicities of the external states, but I'm just going to show the helicity of the intermediate state. There's a factor of I. This unshifted propagator ends up down here. I should put a hat on everything that's shifted. Okay, so that's the final formula, where I just took these amplitudes and labeled them according to their external labels. When I get to this guy in the first amplitude, because of my convention that k runs this way, I need a minus sign to make it an outgoing momenta. And also I need a minus h if h is labeling the helicity going down, whereas here I have the momentum with a plus sign and the h with a positive h. And then you have to sum over all the possible helicities, and if we're doing gluons, you just have plus and minus. So you can use this formula to build up any gluon amplitude you want, just starting with the 3-point amplitudes. And that might seem a little funny because what happened to the 4-gluon vertex? Well, it's really just there for gauge invariance, and it doesn't tell you anything new. So if you have gauge invariance, which is the way you sort of remove unphysical polarizations, so you just have the plus and the minus, then the 4-point vertex isn't doing much for you, except complicating your life sometimes. Now, yeah. Sorry, could you say that again? Did I make a mistake here? This? No, now it's equal. So 0 is equal to this plus this. Okay? So then there's a minus sign when I move it to the other side, but there was also some minus sign in here. Well, there are also a lot of i's flying around that I didn't keep track of. So in this case, it really is an equals. I just wrote the 0 to remind you that it's what we were, the original amplitude. Any other questions? No, it's good. You're on your toes. At this point, there is a secret z. It's being evaluated. To evaluate each term in this formula, you have to take z or z and evaluate it at z sub k. So it's not a free variable, but you have to plug in for it in each term. And that's what we're going to be doing for the rest of the time. Okay. So since we only showed the validity of the BCFW recursion relation when the boundary term vanished, for the case that one gluon was negative and the other one was positive, we have a little issue, which is, what about the case where of n gluon amplitudes where all of the helicities are positive? So those are 0. So you can show this as an exercise. And let me tell you an easy way to show it from Feynman diagrams, but without ever calculating any individual Feynman diagram. So to show this, first show that any tree has at least one epsilon I dot epsilon j. Independent of the felicities, when you draw all the Feynman diagrams for multi-gluon interactions, by looking at the Feynman rules and looking at how the indices are contracted, it's not hard to show that you always have an epsilon I dot epsilon j somewhere. So secondly, in the all plus case, choose the reference spinors to all be the same. Doesn't matter what you choose them to do, choose them all to be the same. And then show that epsilon I plus with that same spinor dot epsilon j plus q is equal to 0 for all I and j. That combined with 1 proves what you want to prove, because all these amplitudes have at least one of them and they're all 0. So now I'm just going to take that result and we're going to now show now we're going to show that the case with 1 minus is 0 using the recursion relation. And I cleverly chose the minus guy to be n, so I can use the n1 shift And then I start drawing these factorization diagrams. So first of all, there's the generic factorization diagram, which has a 1 down here, an n minus up here, and everything else is plus. So this is all plus, all the helicities in this factorization diagram are plus, except for this one minus. Now we got to decide what is this going to be in here. What helicity are we going to have in here? It can't be plus, because looking at this side, we already know from your work to come. So we're violating causality a little bit, but not by too much. Anyway, it can't be plus. That would give 0 down here, so we should make it minus. Now we look up here. So now we say this is 0 by induction. Oh, I forgot to say one thing. I forgot to say n greater than 3. Because we saw earlier that the 3-point amplitude with 2 plus and 1 minus, remember we wrote a formula for it. It had some square brackets in it. That case is non-zero, the 3-point one, but everything above 3 is 0. So we use induction. You can ask what happens at the 4-point level. Maybe I should have done that one first. So we have plus, 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 minus. Let's see if I can get this to work. Well, there's a slight glitch where you have to look at this a little more carefully. And what you find is that this has square brackets, and it's okay. But this one ends up being in the wrong helicity configuration of the two complex helicity configurations. And it ends up, in fact, I did do this one. Okay, so yeah. So this one also wants to be square brackets. But the helicity configuration was found by shifting lambda n tilde. So this was the right-handed spinner. And we were shifting the right-handed spinner in order to put this thing on shell. So we were only adjusting the right-handed brackets. So we must be in the configuration where these are all 0. And then the rule is if you get to a configuration where it's singular, you set it to 0. So this upper part is 0. So the n equals 4 case also checks out. And the generic case checks out. And there are a couple of boundary cases which you have to handle. Because the 3-point cases are always special. For example, when you come down here, you have plus and plus on a 3-point amplitude. You still have to make this minus. This is plus. This one has 1 minus. But you use induction here to say that this guy has 1 minus and the rest plus, and it has to be 0. And then there's also an inductive case on the top end where this one is a 3-point one. This one would vanish up here by this same rule, so you need to have this one be minus. Well, anyway, even if this is a plus and this is a minus, you can still use induction to kill it, because this is a 1 minus and there are fewer legs. So all these other guys go away by induction. So the bottom line is that using the recursion relations and induction, you can show that the 1 minus case vanishes too. So then now we want to do the first non-vanishing case, which was those Park-Taylor amplitudes, which I showed you before, but now we can find them using the BCFW recursion relations, or at least verify them recursively. Yeah?
So it's not really clear why we should put IG to 0 due to, I don't know, reduction process.
Yeah. Well, there's sort of a lousy argument that there are more square brackets upstairs than there are downstairs. So all of these guys are 0 in the...
Why they should be 0? Why they all should be 0?
Okay, there are 2 types of complex kinematics, and you have to ask which one you're in. And in one case, the 3-point amplitude is non-vanishing and it's a non-singular complex number. In the other case, it's 0. The argument why it's 0 may be a little bit sketchy, but because all of the things entering it are 0, and there are more things in the numerator than the denominator. And you have no option for making it into a finite non-zero number because there's nothing non-zero it can depend on. And everything works if you set it to 0. Okay. Any other questions on that? So if not, then we got to do something and actually get a non-zero result. So this time I'm not going to erase things that I can reuse. So we want to show that, let's just call this AJN of the tree amplitude is so I'm only going to show where the minus helicities are, and everything else is plus. So these are the 2 negative helicities, J and N. And this is equal to, and I called it J just because I like to put an I in front of this for who knows what reason. So this is the Park-Taylor formula for the MHV. It's called the MHV tree amplitude. Why is it called MHV? That stands for maximally, whatever. Helicity. I can't write vertically. Violating. You probably can't read vertically either. So this is the maximally helicity violating amplitude because it has a huge number of pluses. And in other words, quarks massless quarks conserve helicity. So if you're in the all outgoing convention, when you have quark lines, those are always written minus plus. Because if you thought of one being in the initial state, then this would really be a plus, and that would conserve the helicity. So you always have minuses and pluses. So if you had only massless quarks on the outside, you would have the same number of minuses as pluses. So things with large number of pluses violate helicity. Why are these called the maximal helicity violating amplitudes? Because they're the maximal non-zero helicity violating amplitudes, because the ones with more violation we just showed were 0. The ones with all plus or just 1 minus. So anyway, these are often called the MHV or Park-Taylor amplitudes. Okay, so we're going to just do this factorization again. We get to reuse the same diagram for the generic factorization, but now we get to put one minus in somewhere. That would be besides n, we also have j as minus, and we're shifting these. So if I put a minus here, I can make this one negative, and the bottom amplitude will be, by recursion, the lower point, a lower point amplitude. We can use the formula by induction, but now the top we now know is 0 because it just has one minus. Okay, so this generic factorization is still 0. That's good. We don't want to evaluate a very large number of residues to get something as simple as the Park-Taylor amplitude. And if you go through the same argument we had before, if you consider the special case where there's a 3-point amplitude on top, you'll see that it's 0 as well, same reason as before. So the only contribution is from k equals 2. So let's draw that one. And just for convenience, we'll assume that j isn't equal to 2. So j is up here somewhere. So this one must be minus because we don't have 3-point all plus amplitude, so this is plus. Okay. So now we need to evaluate the bottom part of this diagram, which was A3 1 plus 2 plus minus k hat 1 2 minus. And that, we wrote down the formula for the 3-point amplitude. So this is the same formula we wrote down before, except that now instead of 3 minus, we have this minus k hat thing, and I'll omit the subscripts because it gets too bulky otherwise. But what was k hat? It was k hat involves a square bracket with k hat requires a lambda tilde. And k hat contains a lambda tilde, but lambda tilde was not shifted. We shifted lambda 1 tilde is not shifted. We shifted lambda 1, but not lambda 1 tilde. And that means that this k hat can just be replaced by either 1 or 2. Also, this one hat we can take the hat off because it's not shifted. So the bottom line is that this thing is I times 1 2 cubed, because we can cancel this, over 2 k hat 1. Up to factors of I from switching these around, which I'm not going to worry about. Okay, so this is the formula we need to plug in from this factor. And in the other factor from the top here, this upper amplitude, we similarly get to plug in the Park-Taylor amplitude over there for a smaller number of legs using induction, and it has k hat 3 3 4 all the way up to n minus 1 n, and then n k hat. There should be hats on top of the n's, but we can remove them for the exact same reason we could remove the hat from 1 on the bottom side, because this involves angle brackets, and those aren't shifted. But we need to have the k hat, keep the hat on that for a little bit. Okay, so now I'm just going to multiply these two expressions together. And so the BCFW formula evaluated just for k equals 2, the only non-vanishing term, says that the AJN should be equal to something like minus I JN to the fourth over 3, 4 up to this. Then there's a 1 over S12, which is there's always an unshifted propagator factor you have to stick in the formula. And then there's a 1, 2 cubed over, I'm going to take these factors and write them. So I have this factor, and I'm not keeping track of signs, so I can flip them around whenever I want. And then I borrow from this formula the nk hat and the 3k hat. And this is also a square bracket times an angle bracket. So now in the denominators we have these k hats, and we're supposed to evaluate them for k hat is k1 plus k2 minus or plus z2 times a spinner lambda 2 lambda n lambda 1 tilde, I guess. But you can see that this z2 isn't going to matter, because here k hat is sitting next to 1, and that means that the lambda 1 tilde gets contracted with lambda 1 tilde, and that gives 0. And over here k hat is sitting next to n, and this lambda n contracts with n to give 0. So the bottom line is we can just plug in 1 plus 2 and 1 plus 2 in here, the unshifted terms. And then in this term, the 1 doesn't matter, and in this term, the 2 doesn't matter. And the stuff that's left over, this becomes a 1, 2, and this becomes a 2, 1, which can be reversed into a 1, 2. So we have a 1, 2 square bracket here, here, and here. And that cancels the square brackets here. So all we're left with was angle brackets, and you can see that we get the ones that were missing from this formula. We were missing n comma 1, and it's sitting in here. We're missing 3 comma 2, 3 and 2, and it's sitting in there. And there's 1, 2 is also missing. So after fiddling around with the factors, you recover the formula. So we just proved the MHV relations by induction. So we have one more amplitude to calculate using BCFW, which we call an NMHV amplitude. And I still have 5 minutes. So let me just do that if there are no questions on this. Or at least start it. Maybe I'll, yeah.
But how do we know that we have, for the 3-point answer, we have square brackets, not triangle?
Yeah, so it was because it was the plus plus minus case. That was the one that had the square bracket formula. At the beginning of the lecture, we wrote down that A3 tree 1 minus 2 minus 3 plus is, never mind the i's, it's an angle bracket formula. Whereas in the plus plus minus case, it's square brackets. And we argued that on a combination of the little group scaling plus dimensional analysis. If you use the wrong one, you don't get the right dimension for. So this is to be used if you're in the kinematics where the angle brackets are non-vanishing. This is to be used if you're in the kinematics where the square brackets are non-vanishing. For this diagram, we're in the right kinematics. We want square brackets because of this rule, and the square brackets are non-vanishing. In some of the argument diagrams that we discarded earlier, we used the fact that we were in the wrong kinematics for the given helicity. But this case, we're in the right kinematics. We get a nice non-zero result. Any other questions? Why don't I care about minus signs? For ease of pedagogy. In the real world, you care about minus signs. You write some code, you care about minus signs. You're trying to keep track of things in a lecture, you don't want to pay attention to minus signs. Do you? I've done it carefully. I've gotten all the signs right once. That's enough. Well, we're almost to the end. We'll see. Anyway, let me just point out the following. How many NMHV amplitudes are there at 6 points? I claim there are really only 3. Remember, these color-ordered amplitudes have a cyclic symmetry because they're coefficients of traces, which are cyclically invariant. So you can cycle things around. You can also use parody if you want to exchange plus and minus. And you can reflect when you flip the whole diagram over, you get a minus sign for each vertex. If you have a 6-point guy, you get an overall plus sign. Anyway, using all those symmetries, there are only these 3 contributions. Although I already gave you a lot of exercises, so this one's optional. You can use the Cochise relations to eliminate one of these. For example, the last one. So there's really only 2 of these that you need to compute, and this is the simplest one, so of course that's the one I will do. I will actually do it tomorrow since we're now past 1 o'clock. But let me just draw the diagrams, and then we'll get back to it tomorrow. So we have k equals 2. So k equals 3 vanishes. We have 3 pluses down here. We do our best to try to make this non-vanishing, but we only have 1 minus, and it's a 4-point amplitude. So that's 0, or 0 on the top too. And then k equals 4 is and then this one wants to be a minus and this a plus. I didn't do, wait, I did something wrong here. Yeah, no, that's okay. So it looks like there are 3 diagrams. However, we don't actually have to evaluate this one. And then next time we'll actually evaluate this one. But the last thing I want to do is just notice that k equals 2 can be related to k equals 4 by the following manipulation. Every time you see a lambda 1 angle, you convert it to a 6 square. So you do this manipulation where you flip like this so that this thing becomes on the bottom. So the 6 minus goes to 1 plus, 5 minus goes to 2 plus, and so on. So you flip it over and conjugate it. And you can map the k equals 2 diagram to the k equals 4 diagram. So we actually only need one BCFW diagram to evaluate this guy too. And we'll do that at the beginning of next time. Thanks a lot. Any more questions, or are people ready for lunch? Well, I'll take questions after.